Greetings and welcome to Precalculus graphs and functions. In this lesson, we're going to focus on transformation of functions. Let's jump in with the transformation of functions. Pretty much what a transformation is when we have a function, let's just call it f, and we manipulate it in a new way, in such a way that it creates a new function. Now, when we transform this primary function, it might be getting wider, narrower, taller, shorter. Those are the transformations that we're going to be doing. We may even be moving it up on our chart or down or left or right. So these are all transformations. So let me show you an example of what a transformation looks like. So we have the function f of x equals the absolute value of x. If we decide to add 2 to this function, so we have a new function g of x such that it equals the absolute value of x plus 2, this is a transformation. That plus 2 transforms the original absolute value of x. Likewise, if we have something like h of x equals the absolute value of x minus 3, again, that's a transformation. We are changing our original type of graph just by manipulating it a little bit. So both g of x and h of x are the transformations of the f of x. Now there are a couple operations that we're going to focus in on. The first two are going to be a vertical and horizontal shift. These are rigid transformations. They don't change the look or the structure of the function itself. It just moves the function to a new location on the graph by shifting it either vertically up or down or horizontally right or left. So let's look at an example. Let's take those f, g, and h functions and take a look at a few values plugged into here. So let's take the x values of -5, -3, -1, 0, 1, 3, and 5, and let's calculate them for each f of x, g of x, and h of x. Now these I'm going to be plotting on the same graph, so f of x will ultimately be in black, g of x will ultimately be in a red color, and h of x will be in a purple color when I actually graph it. -5, the absolute value of -5 is 5. -3, the absolute value of -3 is 3. -1, well, the absolute value of -1 is 1. 0, the absolute value of 0 is 0. 1, the absolute value of 1 is 1. 3, the absolute value of 3 is 3. And 5, the absolute value is 5. So I'm going to plot the positions -5, 5, -3, 3, -1, 1, 0, 0, and so forth. And that will be my function f of x. Now if I plug each of these x values into g, I have the absolute value of -5, which is 5, plus 2 is 7. So you'll see it shifts from a 5 where it was to now a 7. And again, -3, the absolute value of -3 is 3. 3 plus 2 is 5. It shifted from a 3 result to a 5 result. The absolute value of -1 is 1. 1 plus 2 is 3. We shifted from a 1 to a 3 for our result. And you can follow it down where you can see we're shifting our values. 0 became a 2, 1 became a 3, 3 became a 5, and 5 became a 7. Now let's just quickly look at a few of these for hx. I'm not going to run through every single one. I'm going to take my -5, take the absolute value of -5, minus 3 is 2. So I'm putting in -5 in here. Absolute value of -5 is 5. 5 minus 3 is 2. I'm going to do one more. -3. The absolute value of -3 is 3. 3 minus 3 is 0. So originally we were at a 3. Now we've shifted to a 0. A 1 shifts to a -2. A 0 shifts to a -3. A 1 shifts to a -2. A 3 shifts to a 0. And a 5 shifted to a 2. Now, if you see, from a 5 to a 7, we went up 2. A 5 to a 2, we went down 3. So anytime we have like a plus 2 out here, it's going to be a shift up, and anything that's a negative is going to be a shift down. So now let's take a look at what these actually look like. Here's our original function, f of x. It looks like a v starting at 0, 0, or at least going down to 0, 0. And it shoots off to the right, and it shoots off to the left. G of x was the absolute value of x plus 2. It actually shifted every single point up 2. So here we were at a 0, we shifted up 2. Here we are at a negative a 1 on the y, it shifts up to a 3. Here's a 1 on the y, shifts up to a 3. So all of these points shift up 2 locations on the y. Now, h of x is the absolute value of x minus 3. It shifts everything downward. So here we were at 0, we're down to 3. We were at 1, we're down to negative 2. So if I have this graph, f of x, and I understand what this minus 3 does, a shift, I don't really have to do any math. What I can do is just shift all of these points down 3 on the y, and I'll have my new graph. Understanding shifts are going to make your math go a lot faster because there'll be a lot of calculations you won't have to do. Because if you understand, oh, I just move this point up 2, move this point up 2, move all points up 2, then you're done with math. You're moving a point. Likewise, if you understand that this means move down 3 for all points, again, it's less math you'll have to do in the long run. I want to take a look at what a vertical shift looks like just generically. If we have some function, we're going to let our d value be greater than 0. If we have some second function, g of x, and that is our f of x plus some value d, remember d is greater than 0, then the graph is actually just f of x shifted d units up. And if we have a minus d, then the graph is still f of x, but it's shifted d units down. When you look at it from the point of view of the actual point on the graph, our f of x would be the point xy, but our g of x would be x comma y plus d or x comma y minus d, depending on what we're adding at the end of our function. So let's take a look at not vertical shifts this time, but horizontal shifts. And we have our basic function of a parabola, which is f of x equals x squared. And all I'm going to do is I'm going to change it slightly. G of x is going to be x minus 2 all squared, and h of x is going to be x plus 3 all squared. So here's what's going to happen. I'm going to go ahead and draw a table, fill in our data, our points, and then I'm going to graph it. So I've picked out a handful of points to calculate. -4, -3, -2, -1, 0, 1, 2, 3, 4. So these are the values that I've just decided to use. Really, you could have used anything that you want, but I've chosen these values. I'm not going to run through all of these. I am going to run through a couple of them going across. So take -4. If you square it, -4 times -4 is -16. For g of x, that's going to be -4 minus 2, which is a -6. -6 squared is 36. So we were originally a 16, now we're 36. Now let's take a look at h of x, which is this plus 3. We start with -4, add 3, and we get -1. -1 squared is 1. Originally, we were 16. Now we're at a 1 on our y value. All right, let's do one more row, and then you can pause the video and take a look at all of these if you want, but I'll just go through one more row. Let's take the x value of -3. -3 squared is 9. So that would be -3, 9 would be our point for f of x. For g of x, it's going to be -3 minus 2, which is negative 5. Negative 5 squared is 25. So my point would be negative 3, 25. All right, one more. Let's take that negative 3 and throw it in h of x. Negative 3 plus 3 is 0. 0 squared is 0. So the point would be negative 3, 0. Now take a moment and take a look at all of the points. These are each individual points, like f of x will be negative 4, 16, negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. That's what we're going to use in terms of points to plot f of x. Again, I'm going to do f of x in black. For g of x, it's going to be negative 4, 36, negative 3, 25, negative 2 and 16, negative 1, 9, 0, 4, 1, 1, 2, 0, 3, 1, 4, 4. And that I'm going to do in red. And then lastly, for h of x, where it's x plus 3 squared, we're going to plot the points negative 4, 1, negative 3, 0, negative 2, 1, negative 1, 4, 0, 4, 1, 9, 2, 16, 3, 25, 3 is 36, and 4 is 49. Can't even read my own writing. These are what I'm going to plot this time. And you'll see, look at the red one versus the red, or look at the black image versus the red and the purple. Okay, so here's my black graph. That's my f of x. And when I said minus 2 for my g of x, it actually shifted it 2 units to the right. That's all it did. The shape is exactly the same. All this does, this minus 2, shifts f of x. If I picked it up and moved it over 2, it's sitting where g of x is. Now for h of x, that's sitting x plus 3. This plus 3 shifted our f of x to the left 3 positions. So every single point on f of x, you could literally just pick up this graph and move it 3 positions to the left, and that becomes h of x. So just take a look at that. When you have x minus 2, it shifted it 2 places to the right. X plus 3, 3 places to the left. So our shifting is left and righting. All right, so here's the bottom line. Let's let this value c be greater than 0. And we're just going to focus on g of x being something that looks like f of x minus c. Well, if it's minus c, it's shifted c units to the right. If it's plus c, the graph is shifted c units to the left. There's no change in the shape and the look of f of x. It's just shifted either left or right depending on what c is. If it's minus c, it's to the right. If it's plus c, it's to the left. So let's look at something that looks combined, not only vertical but horizontal shifts in the same problem. So here we go. We want to sketch the graph of g of x, which looks like f of x plus or minus c plus or minus d. This plus or minus d is on the outside of those parentheses. The plus or minus c is on the inside of the parentheses. So here's an example. G of x equals the square root of x plus 2 minus 3. The first things we really want to do is identify the c and the d. Remember, the c is the horizontal shift and the d is the vertical shift. So here is our original f of x. Our original f of x is just the square root of x. So take off that plus 2, take off the minus 3, and we get this simple square root of x function. This is our original f of x. We do want to talk about what our domain and range is here, because that's going to limit what our other graph is also going to look like. Our domain for a square root function is 0 to infinity, including 0, and our range is 0 to infinity as well. So the first step is we really need to identify the graph that it's based off of. So if g of x is the square root of x plus 2 minus 3, where is the original graph in that? Well, it would be the square root of 2. Just want to raise this up just slightly. There we go. Give me some more space here. Second step is to figure out, well, the position constants, which are c and d. Okay, well, the square root of x plus 2 minus 3, the thing that's touching the x is the c. So c is positive 2, and d is the 3 sitting out here. So c is 2, d is 3. When c is positive, we need to figure out, is that lefting or righting? And the d is here minus 3. Is that going to be upping or downing? So we got to figure out, how are we going to move this graph around? So if f of x minus c, we're going to shift to the right. Well, it turns out we're not minus c here, we're plus c. So we're going to be in a situation where we want to move our graphs 2 units to the left. Okay, so this 2 units will go to the left. Then we want to look at the plus d or the minus d. In this case, we're minus d, so that's going to shift d units down. So we're going to shift 2 units to the left, so anything that's sitting right here is immediately going to be moved to the left. And with the d, we're also going to shift it down 3. So let's take a look at what that ultimately looks like, f and g. So here we go. If I knew the square root function looked like this, then all I'd have to do is move this point, 0, 0, 2 to the left and 3 down, and that's my new point. And then likewise, I would move the next point, which is 1, 1, 2 over and 3 down. Move this point, 2 over, 3 down. And by the time that you move every single point on f of x, you get to g of x. Okay? So you move everything to the new location just by shifting. I didn't do any math here. Besides f of x, I knew 0, 0, so the square root of 0 is 0, the square root of 1 is 1, and I chose 4, and the square root of 4 is 4. So our square root of 4 is 2. So I did know those basic without having to do the rest of the math in G. I picked some nice points and I just graphed the square root function. But then once I have the square root function, using these position values, I can start manipulating where my graph is. There's another type of rigid transformation, meaning rigid. We're not manipulating the graph itself, we're just moving the position. And these are reflections. It's going to reflect the graph about an axis, either the y-axis or the x-axis, and maybe sometimes both. So let's take a look at comparing two functions. We'll just say y equals f of x and y equals negative f of x. So let's go ahead and let f of x actually be a function x squared. Okay, we've already graphed this. If I can find it, let me graph. Okay, so we already graphed this. It's a parabola. So here's our f of x right here. Okay. We know it's a parabola, and if we have a function g of x, which is actually the negative of f of x, so that's negative square root of 2. Here's what's going to happen. I'm going to show you this all at once. You can slow down the video if you want. All this is doing is plugging in some x values into f of x and figuring that out, plugging in some x values into g of x and figuring out the result from there. So negative 3 squared is 9, negative 2 squared is 4, negative 1 squared is 1, and so on. Negative 3 squared is 9, but the negative of 9 is negative 9. negative 2. Negative 2 squared is 4, but the negative of 4 is negative 4. And negative 1. Negative 1 squared is 1, but the negative of 1 is negative 1. And I'll let you finish up all of the points that we're going to plot. So for f of x, I'm going to use negative 3, 9, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, and 3, 9. For g of x, I'm going to use negative 3, negative 9, negative 2, negative 4, negative 1, negative 1, 0, 0, 1, negative 1, 2, negative 4, and 3, negative 9. And let's take a look at what that looks like. So here's our f of x. That should look pretty familiar. And in fact, g of x is a reflection across the x-axis. So this negative forces everything to be a reflection. Like if I sat a mirror right here, it would be a reflection. And it literally, if I folded this in half and laid it right on top of one another across the x-axis, that's what a reflection is, across about the x-axis. If it's the y-axis, then it's going to be a reflection this way. But this is a reflection the x-axis. All right, let's take a look at the actual rule for reflection about the x-axis. When we are given a graph, g of x, and that equals negative f of x, then the graph is reflected about the x-axis. So if we have a point xy, which is on the f of x graph, then we know the point x, negative y, is on the graph of g of x. So your y, where it was positive, is now negative, and vice versa. It's going to change the signs. So let's compare now a different scenario. Y equals f of x and y equals f of negative x. In the previous example, the negative was on the outside of the function notation. This is on the inside of the function notation. You might be able to anticipate where we're going with this. Let's let our function this time be this square root of x. We've already seen what it looks like, and it looks like this guy. That's our square root of x. Okay, and we're going to let g of x be the function f of negative x. So anywhere we see an x, we are going to put a negative x. So we become the square root of negative x. Now don't worry about this, that there's a negative inside the square root. We still have options here. So hang tight and let's take a look at some example values. Okay, here are my x's. Here's my f of x, which is the square root of x. Here's my g of x, which is the square root of negative x. I'm going to take the value negative 4. I'm going to plug it in and I get the square root of negative 4, but in the real numbers that is undefined. But for g of x, I get the negative 4, which is really the square root of 4, which is 2, so that's permitted. In f of x, a negative value is not permitted, but in g of x, a negative value is permitted. I'm going to try negative 1. Negative 1 in f of x is the square root of negative 1. In the real numbers, it's undefined, so there's no value here. For g of x, though, that's negative 1, which is the square root of 1, which is 1. That's good. Let's try 0. All right, 0. Square root of 0 is 0 for f of x. The square root of negative 0, well, that's really the square root of 0, which is 0. And you can see it actually, for 1, f of x is finely defined, whereas g of x is undefined. Likewise, with positive 4, for the function f of x, it is defined. The square root of 4 is 2, so that is a point I can plot. But with g of x, that's a square root of negative 4, it's undefined, so there's no point I can plot here. But let's take a look at these two functions. As it turns out, g of x is the reflection of f of x along the y-axis. It's the mirror image of it. So where f of x goes towards the right, g of x goes towards the left. It is a reflection about the y-intercept. or y axis. Now let's just clean it up, finish it up. If we have the graph of g of x equals f of negative x, then our graph f of x is reflected about the y-axis. That means it's going to be this mirror image around this point right here. Meaning, if xy is in the function f of x, then negative xy is on the graph of g of x. How does that help us? Well, if we know that negative xy is on g of x, then we only need to figure out f of x, and then any x value we get here, as long as it's valid, we can just take the negative of it, and it's less work that we have to do mathematically. Always think about, hey, this is going to save me some time in the long run once you learn these rules. Now we can combine these transformations. So let's take a look at an example. Y equals negative absolute value of x minus 2 plus 3. Now when you look at the core of what would this be if it was just f of x, nothing fancy, nothing crazy, it would probably come from y equals the absolute value of x. Now I'm going to go ahead and reveal, here we go, do step by step. So here's our original function, f of x. That's going to be the absolute value. The first thing I want to do is look at this inside minus 2. This inside minus 2 means, hey, shift everything to the right 2 spots. So I'm literally going to move every single point 2 to the right. And I get this new function, the absolute value of x minus 2. Now, I get the fact that I'm not done yet, right? I've just shifted everything over 2, and I still have a few more things to work with. But it's a starting point. And let's face it, have I really done any math? Not really. I knew what the absolute value function looks like, and even if I didn't, 0, the absolute value of 0. 1, the absolute value is 1. Negative 1, the absolute value is negative 1. It's at least math that I can do in my head. So I'm going to work with this original function and start manipulating it using these transformations. All right, we shifted everything 2 to the right. Now, what we should do next is this negative. What does that negative do? That negative makes it a reflection about the x-axis, meaning literally flipped everything that's here upside down, like you're looking at it into a glass mirror. So here we've already done this minus 2, moved everything over 2, and then we're going to do this reflection and literally push everything where this was a 3, 1, it's now a 3, negative 1. You've done all the negatives on the y values, not on the x values. All right, third step. Now we're going to do that plus 3. This is always the last shift that we do. So minus or negative the absolute value of x minus 2, and we're going to shift this 3 up. So we're going to take this original graph of the negative absolute value of x minus 2 and shift everything up 3. This will be our final function that we graph. So where I was at 2, 0, well, 0 plus 3 is now 2, 3. So everything gets pushed up 3 points. And that's it. I didn't do any math. I didn't do any tables. I just did a few steps to graph this. If I was going to do this, I probably would sketch out 3 different graphs and then end up with my final graph, right? So there is a proper order to this. We'll run over all the proper order in just a moment. When do you do which transformation? But it's pretty much in that order. You'll do any horizontal shifting, then you'll do any reflections, and then you'll do any vertical shifting. It's pretty much in that order. All right, let's look at another example. We want to graph y where it's the absolute value of f of x. Okay, I'm going to use the function f of x equals x plus 1 all squared minus 4. And we're going to sketch this absolute value of our function f of x. And remember, f of x is x plus 1 all squared minus 4. There's a whole bunch of transformations. But think about what is it, the function that we're really doing without all the fancy. If we get rid of this plus 1 and we get rid of this minus 4, we're really just doing x squared. All right, x squared. First step, let's sketch our f of x, meaning the basic, well, in this case, I just graphed it, but we could do the basic parabola, and then we're going to move to the left 1, but down 4. So ultimately, move over 1 to the left and down 4 for all of our points, and we will get our new function, or our resulting function. Now here's the problem. If I want the absolute value of f of x, then any y value that's negative is not permitted. So we're going to have to reflect this part of our graph upward. Any point that we have here is now, so here's 1, 2, 3, 4. This is -1, -4. This can still be -1, but it cannot be -4 on the y. But it will be +4. So this piece of the puzzle will be reflected along the x-axis. And when we do that, we now have this little part, instead of dipping down, it's going to create a hill. It creates a hill. And this is our final result of our absolute value of f of x. So pretty much 2 steps. Graph the original one, and then anything that's below the x-axis has to be reflected up. Any negative y values become positive y values. Another type of transformation we want to talk about now is actual distortion of our graph. It is non-rigid. When we're talking about rigid, we're just talking about location. We're not really messing around too much with the shape of the graph. But when we're working with stretching or compressing our graph, this is distorting our graph. Consider y equals a times f of x, and also y equals f of x times f of b of x. These two things are going to distort our shape. One is multiplying by a value to our function, and the other is multiplying our value of our function by another value. Our original function is going to be f of x, but you can see we have this distortion right here in front, a, and this distortion within the function, we have a b. Okay, stretching and compressing our graph vertically. Let's let our f of x be our absolute value of x. Our g of x is going to be 2 times the absolute value of x, and h is going to be 1/2 the absolute value of x. So ultimately, here's what this is going to do. Anytime that we're stretching or compressing our graph vertically, that's going to change the shape of our graph. So here we go. Since g of x is 2 times the absolute value of x, this means it will grow twice as fast, meaning it's going to be skinnier. If it grows twice as fast, then it's going to be skinnier than our original graph. Versus h of x is 1/2 times our absolute value of x, and therefore it will grow half as fast. In other words, it's going to get fatter than our original graph. So let's look at it visually. Here is our f of x. G of x is growing faster, so these bars are skinnier. They're moved in a little bit. You can see everything's moved in. H of x is growing half as fast as the regular f of x, and therefore it takes longer to build up, meaning it's kind of fatter. There's a larger opening between the arrows. Larger number will make it grow skinnier. Smaller number will make it grow slower. It's in essence fatter. Okay. Now here are our values. If you wanted to sketch them out, just compare the f of x, g of x, and h of x. If our result is 2 with f of x, we grew twice as fast with g of x and half as fast as h of x. And that's kind of all this says as well. Numerically, you can see 2, oh, this is 4. 1, oh, this is 2. 0, that's of course 0. 1 is 2, and 2 is 4. 2 is 1, so it's half of it. 1 is 1/2, that's half of it. 0 is 0. 1 and 1/2, that's half of it. And 2 and 1 is half of it. So if you have a fraction, it's going to grow half, or I should say any fraction is going to be growing slower, therefore your graph is distorted outward, fatter, versus a larger number, it is growing faster, so it's thinner. Vertical stretching is where when we have this a in front, so we had 2 here and we had 1/2 here. If it is a vertical stretch away from the x-axis, that's when your a value is greater than 1. We had a 2, so it went faster away from x. A vertical compression towards x is if it's between 0 and 1. Right? Now, we didn't talk about what happens if it's negative. Well, first you're going to graph what happens with the stretching and compressing, and then of course since it's negative, it's going to be a reflection. So it won't be pointing up this way anymore. It will be downward if it's negative. So all of these, if these were negative, if this was a -2, a -1, and a -1/2, they would all be facing downward, not upward. Okay. With either one of these, stretching and compressing, the x-intercepts actually stayed the same, but the y-intercepts may change. X-intercepts stay the same, but the y-intercepts might change. It's not a guarantee, but they might change with vertical stretching. Let's take a look at a couple of examples. Here we're stretching vertically. Our original graph is right here. And so this is f of x. When I have y equals a f of x, it's going to stretch upward. Now if you notice, the x-intercept stayed the same, but the y-intercept did in fact change. When our a value is somewhere between 0 and 1, in other words a fraction, then it squats down. It moves towards the x-axis. This is away from the x-axis. This is towards the x-axis, and it gets flatter, right? So now here is our new, same function as it was before, but now we have this new function. Still, x-intercepts are the same, but the y-intercept actually is different. Again, that's not a requirement that the y-intercepts change. It just so happens in these examples it did. So let's compare. That was with our growth factor, our compression and stretching, where it said y equals a f of x. Now let's take a look at that second option where we had y equals f of x and y equals f of b of x, b times x. So now our growth and our stretch and compression is on the inside. Well, you might be able to take the leap. If this is talking about vertical stretch, well, this is probably talking about horizontal stretch. And indeed, that is what we're talking about. Horizontal compression and stretch. We're going to let our b value be greater than 0. And therefore, anytime that we have like an f of x, we can find g of x by multiplying everything by 1 over b. It's 1/8. 1/8 of the size. So if I had a 1 here, that would be 1 over b if the result would be. Let's look at an example. I know it's a lot of words here, so let's actually take a little bit of an example, and I may have jumped the gun on this one. So just like we had stretch vertically if a is greater than 1, and if it's between the 0 and 1, it's a compression. For horizontal, it's actually the opposite. For horizontal, because it is the reciprocal of b, The horizontal stretch away from the y-axis is when it's 0 to 1, but a horizontal compression towards y if b is greater than 1. Right? So we get closer into the y if this b is greater than 1, and stretches away from the y if b is anywhere between 0 and 1. All right, so what we're going to do is we're going to graph our original function, and then we're going to stretch it if necessary or compress it. Just like if a was less than 0, we do have a circumstance where sometimes b is less than 0. And if that's the case, we're going to reflect about the y-axis. So it's going to be that mirror image this way, not the x. Okay. So if we have the point xy is on our normal function, f of x, then the point 1 over bx, y, is on the g of x, where g of x equals f of b times x. I know it's a lot. I'll get you into an example. Hopefully you'll be able to see where everything's coming from. In horizontal stretching and compressing, the y-intercepts actually stay the same, but the x-intercepts might change. Okay, so that might change. Let's actually look at a function, and let's do the stretching and compressing horizontally. So let's say this is our original function. There's no, function in terms of, oh, it's x squared. I literally will draw the function, and where you see our point, -2, -1 is right here, 0, 0. Then we kind of loop up to 1, 3, and then down to 2, 0. This is our function. Now let's take a look at a couple of examples where we're going to do some horizontal stretching. Let's take the function and do 1/2 x. Let's take the function 2x, and let's take the function with a -2x instead of just f of x. Building from this original function, if we are 1/2 x, that means, covered this up, we're going to be twice as far away from our y-axis. So where we were at -2, we're now going to be at -4. None of the y's change, so I'm at -4, 1 now. 0, 0 hasn't changed because this is going to be 2 times 0, and 2 times 0 is 0. I'm taking the reciprocal. This is going to be, well, the reciprocal of 1/2 is 2, so this is 2, 3. So I now become 2, 3. I'm stretching it away from the y. And where I was at 2, 0, I'm going to take 1/2, take the reciprocal, which is 2. 2 times 2 is 4, so my new point is 4, 0. I didn't mess around with the y, I just messed around with the x value. Now here for the b, I'm at 2x. That means everything is going to be halved. All my x's are going to be halved. So if I'm at -2 here, half of -2 is -1. Half of 1 is 1/2, and half of 2 is 1. So I'm actually going to squeeze that in. It is a compression. So my point that was at -2, 1 is now at 1, 1. My point that was at 1, 3 is now at 1/2, 3. And my point that was at 2, 0 is now at 1, 0. So you take the reciprocal and you manipulate your x values. Now here, our x value is, or our value that we're going to deal with, is reflected as well as compressed. So we have a -2x. Well, in essence, it's this, but flipped upside down. So I'm going to use this guy and literally just flip all the points along the y here. Okay? So where I was -1, 1, that's going to flip over to the other side where it's 1, -1. So here I have a -1, it becomes +1. Where I had 1/2, that's going to become -1/2. And where I have 1 is going to be a -1. So I'm literally just flipping this over the y-axis. That's pretty much manipulation. You just have to remember it's the reciprocal of the value in front of the x is how you're going to manipulate it. All right, you have come to the point that this all culminates to. We're going to put all of this together. We're going to put vertical shifts, horizontal shifts, reflections, stretches, horizontal stretch, horizontal compression, vertical stretch, and vertical compression, all in one problem. And we're going to figure out what is the possible order of dealing with a problem like y equals AF time of B of x. Let me see if I can say this correctly. Y equals A times F of BX minus C plus D. So we have vertical shifts, we have horizontal shifts, we have compressions, we have reflections. All of that is going to be in this problem. Our original problem looked like f of x. Here's one possible order on how to conquer this problem. First things first, think about your original function. In this case, our original function is just f of x. For every x, there is a y. Step 1 is going to be the horizontal shift. That's this minus c. And if it is minus c, in fact, it is minus c, then any of our x values become x plus c's. We leave the y alone. Second, our stretch or compression. That's where we have this b value out front. And if we have a b value out front, again, that deals with the x. We're going to divide every x by b value. And keep in mind that it's really x plus c is our new x value. But let's just take a look at x's. Will be divided by b. So if there was a 2x, then it would be divided by 2. If it was 1/2, well, then take the reciprocal. It would actually be multiplied by 2. But y is still the same. We're not messing with y yet. The third step would be any reflections about, stretch and compression. We still have to deal with the y stretch and compression now. That's the a out front. If we want to deal with the absolute value of a, because the negatives are reflections. They are not stretch and compressions. So we're just dealing with the a. Any a we have out front, we're going to multiply y by. So if we have a 2 out front, we're going to multiply it by 2. If we have a 1/2, we'll multiply it by 1/2. Now we're dealing with reflections. If a is negative, then you reflect all your x's, right? Sorry, if b is less than 0, then you reflect all your x's. If a is less than 0, you reflect all your y's. B goes with x, just like it did up here. A goes with y, just like it did right here. Finally, we do vertical shift. We do this d plus d, and that's going to be take your y and add your d. If this was negative d, you would just say minus d. It's a straight shift. So are you ready? Here's a big one. Let's take a look at this multiple transformation. Our function f of x is negative 2 times x minus 1 all squared plus 3. We're going to do this in steps. Our first step is to figure out what is the primary function that this beast of a problem came from. And it looks like it's x squared, or at least one of them could have been x squared. So if our original equation, y equals x squared, then our first thing is our horizontal shift. We want to shift everything over to the right 1. So here's our original graph. We're going to literally pick this up and move everything over 1 space. Shift 1 to the right. Next step. Take a look at the multiplication of 2 out here. Okay. So I'm going to just cover that up really quickly so you don't need to see step 3 yet. But let's deal with this stretching factor. And that means everything is stretched by a factor of 2. So where our point was 2, 1, we are now 2, 2. Where we were 0, 1, we're now 0, 2. We're multiplying all the y's by that 2. Okay? We're stretching it vertically. Next is step 3, where we have this minus 2. Well, that means it's reflected about the x-axis. It means we're going to flip this guy downward. So where we were 1, 0, we're still 1, 0. But where we were 0, 2, we become a 0, negative 2. All the y's are flipped to the opposite sign. Okay, next step. Step 4 is where we have this plus 3. This is our vertical change. So everything is going to move up 3 positions. I'm going to literally pick this guy up and move it up 3 positions. Where I was 1, 0, add 3 to the y, I wrote that wrong. That should be 1, 3. I had a dyslexic moment. Where I was 0, negative 2, I'm now 0, 1. Where I was 2, negative 2, well, negative 2 plus 3 is positive 1. Where I was 1, negative 8 plus 3 is negative 5. And 3, negative 8 is 3, negative 5. Everything moves up 3 positions. It is a vertical shift. So we did, in total, we did a horizontal shift for step 1. Step 2, we did a vertical stretch. Step 3, we did a reflection. Step 4, we did a vertical shift. Vertical shift is always going to be the last thing you do. All right, let's sum this up, all the main facts that we did talk about with transformations. We are going to be talking about transforming a simple function like y equals f of x. We have vertical shifts. This is when our d value is greater than 0. If it looks like f of x plus d, it's going to be up d units. So our results would be on the y change, not the x. If it's f of x minus d, then it's down d units. Again, that's on the y. It's a vertical shift. A horizontal shift is when we have a c value. That's going to be f of x minus c. If it is minus c, it's to the right. If it is plus c, it is to the left. It's the opposite symbols. I get the fact that it does look a little strange that it's opposites, considering the d's are actually, positive is plus and negative is negative, minus. Reflections, we have y equals negative f of x. Well, that's going to reflect all your y's. That's around the x-axis. And if it is inside f of negative x, that reflects around the y-axis. All your x's will become the opposite symbols. Vertical stretching or compressing, that's when we have a value outside of our function at the beginning of our normal function. If a is greater than 1, it's going to stretch away from the x-axis, and if it is between 0 and 1, it's going to compress towards the x-axis. And remember, it can be negative, and then it's a reflection on top of this stretch or compress. Okay, so it's a reflection as well as the stretch or compress. Then we have horizontal stretching. Horizontal stretching is when you have the multiplication against the x, so f of b of x. If it is 0 is less than or equal to, or less than or equal to b, 0 is less than b is less than 1. So let's say a fraction or a decimal, it's stretched away from the y-axis. If b is greater than 1, it compresses it towards the y-axis. It makes it this way versus that way. And our x is manipulated. Again, if b is less than 0, then you still stretch or reflect about the y-axis, but then it's reflected. It's going to, all your y's are negatives, are the opposite of what they are. So it reflects around the x-axis. Compresses and stretches towards the y, but it reflects around the x. Last little bit, hang in there. To summarize how you would do a transformation sequence, here's what you do. You have this goofy function. It looks like crazy stuff, but First things first, figure out your original function and go ahead and graph it. Okay. Next, you're going to deal with your horizontal shift, your C value. Then your horizontal stretch and compression, that's your B value. Then your vertical stretch, which is your A value. Then you're going to reflect it just if you have a negative A value. And then you're going to do your vertical shift, which is your D value. So in order, C, B, A, then D, and any reflections in there before you get to the D. But you always do your vertical shift last. So once again, horizontal shift, that's your C, left or right. Horizontal stretch, that's going to be your B value. If your B value is negative, then you'll want to do a reflection as well. Then you do your vertical stretch and compression, that's your A value, and then reflect if it's less than 0. And then you do your vertical shift. Yeah, I get the fact it's a lot of steps, but ultimately you could just throw in a value of X and plug it in and see what happens. It's just if you know what the basic function looks like x squared, if you already know what that looks like, then you're just manipulating that function and it would save you quite a bit of math. Yeah, so I think that's it for this video. Until next time, be seeing you.